Let's evaluate some infinite limits. First, let's find the limit as x approaches 3 from the right of the expression x plus 2 divided by x minus 3. Notice that you cannot just simply do direct substitution, because if you plug in 3 for x, this will produce a 0 in the denominator. Now, if we plug in 3 for x in the numerator, we would get the value 5. So intuitively, let's try to evaluate this function by using direct substitution to help us. So if I plug in 3 in the numerator, I'll get 3 plus 2. In the denominator, I'll get 3, it's kind of we're approaching 3 from the right. And so just intuitively, this expression is 5 over a positive 0. And what I mean by a positive 0 is the numerator is approaching 0, but it's approaching 0 from the right. So the numerator has small, very small positive values. The numerator, as x approaches 3 from the right, is approaching the number 5. So since 5 is positive, the denominator is approaching 0, but by approaching it from the right, we see that this fraction should be going to positive infinity. So this whole fraction will be numerically a very large positive number. So we define this limit to equal positive infinity. Now let's consider the limit of the same fraction, but as x approaches 3 from the left. Again, the numerator will be approaching the number 5 as x gets closer to 3. The denominator will be going to 0, but only with negative values, slightly negative numbers. So we have this fraction, the numerator is going to 5, the denominator is getting closer and closer to 0 from the left, so the whole fraction will be negative, and it should get arbitrarily large negative as x gets closer and closer to 3 from the left. So this expression we would write negative infinity. Okay, so it's important to note that these expressions like 5 over 0, these are not the answer. These are just ways to use our intuition to help us determine if the limit is either going to be positive infinity or negative infinity. Now let's consider the limit as x approaches 1 of the expression 2 minus x divided by the quantity x minus 1 squared. Again, we can use direct substitution just to help us evaluate this limit. We notice that if we plug in 1 for x in the denominator, we'll be dividing by 0. So you can't use direct substitution to evaluate this, but it will help us. So let's plug in 1 for x. In the numerator, 2 minus 1 will equal 1. And in the denominator, as x approaches 1, x minus 1 goes to 0. And whether x approaches 1 from the right or to the left, when I square the denominator, it'll always be positive. So the denominator is going to 0 positively. So the numerator is approaching a fixed positive number, 1. The denominator is going to 0 positively. So the whole expression will be getting arbitrarily large positive. So the limit we would write equals positive infinity. In this example, we're going to find the vertical asymptotes of the graph of the function -1 over x squared minus 4. So we need to determine if this function has any infinite limits. In order to do this, we're going to factor the denominator of this expression. After we factor this expression as a difference of squares in the denominator, we notice that the function is not defined when x equals 2 or x equals -2. So whenever we're dividing by 0. So in this example, we see that the numerator does not have any common factors of x minus 2 or x plus 2. So the graph should have vertical asymptotes both at x equals 2 and x equals -2. So let's look at this more carefully. Let's look at the limit of this function as x approaches 2 from the right. Let's think about direct substitution. The numerator is getting closer and closer to -1. As x approaches 2 from the right, x plus 2 is approaching the number 4. And x minus 2 is approaching 0, but it's approaching 0 positively because x is slightly bigger than 2. So this fraction, the numerator is approaching -1, the denominator is approaching 0, but positively. So this whole expression, we would say the limit is -infinity. So again, so this verifies the fact that the line x equals 2 is a vertical asymptote. X equals 2 is a vertical asymptote of this graph. Now let's consider the limit as x approaches -2 from the right. In this expression, again, the numerator is going to be approaching -1, and the first factor in the denominator, x plus 2, will be approaching 0, because -2 plus 2 is 0, but since I'm looking at values slightly to the right of -2, x plus 2 will go to 0 positively. And then x minus 2 will approach the quantity -4 as x approaches -2. So look at this expression. The numerator is getting closer and closer to -1. The denominator is getting closer and closer to 0. We have a factor approaching 0 positively times -4. The denominator will go to 0 negatively. There's a total negative factor in the denominator. So a -1 in the numerator divided by 0 negative the negatives will cancel out, and this limit will be plus infinity. Now this limit still is an infinite limit, so therefore the vertical line x equals -2 is also a vertical asymptote. So the key idea is to look at when the denominator of this function would equal 0. This is where we could potentially have vertical asymptotes of the graph. So in other words, for this particular function, that's why we looked at the limit as x approaches 2 and as x approaches -2. Now let's consider the limit as x approaches infinity of the expression x squared minus x. Now, limit laws won't be able to be applied here because if I separate this as the difference of two limits, I'll get infinity minus infinity because x squared is approaching infinity and negative x is approaching negative infinity. So we can't apply the limit laws. However, we can use a little bit of algebra to help us evaluate this. Let's factor this polynomial by factoring out a common factor of x. So now consider the limit of the product x times x minus 1 as x goes to infinity. X is going to infinity. X minus 1 is still approaching infinity. So when I multiply two infinitely large numbers together, the product will still go to infinity. So the limit here, we could actually write infinity. So this is an example of an infinite limit at infinity. That is, the values of the function get arbitrarily large as the value of x gets arbitrarily large.